right, hello, this is Mr. Collins,
It's Miss Bratcher.
and here's episode 2 of our weekly wrap up that we are calling the Formative Word. So before we jump into the material, the stuff that we want you to know and be darn sure you're ready to produce on a test, let's talk about some big announcements just so you guys know what's going on. So there's a test next week. That's going to be the 20th and the 21st for A and B days. So to prepare you for this, there's actually 3 big things we want you to look at. Today, in-class relay race, the 24 problem set, which is right now posted to the G Drive, will give you a really good idea about the type of thing you need to do. Khan Academy, we recommended several things in Khan Academy. Some people already had them done, but if not, you have like 7 different things that cover all the skills that you're going to need to be able to display on that test. And then, of course, the in-class review that we will do the 18th and the 19th, the days before the test. So, guys, don't wait on this. There's a lot going on. There's a lot of tests up in front of you. Don't procrastinate. All right. So we got just 3 little things for you today. Mrs. Bratcher, if you want to take away, let's talk about this girl getting her shadow cast.
Okay, so we have a girl that is 160 centimeters tall, stands 360 centimeters from a lamppost at night. Her shadow from the light is 90 centimeters long, and how high is the lamppost is the question. So right off, I don't know about you guys, but I personally cannot think of this in my head, so I'm going to draw a little diagram to help me visualize what's going on here.
Woo, picture!
Okay, so right off it says this girl standing here is 160 centimeters tall. Okay, and she stands 360 centimeters from a lamppost. And her shadow from the light is 90 centimeters. Okay, so it's going to hit right at this point, and her shadow, or the light comes right here. So actually this point. And then let's move this on down. Whoops. Okay. And then the question is, how tall is this lamppost here? So how tall is that? Okay?
So before you get to Ms. Bratcher, I mean, I just want to emphasize, like, the idea of drawing a picture is something we saw people not drawing pictures, which is crazy. Like, drawing a picture is the easiest way to understand what's going on, what numbers to use, and what position. Because I guarantee if you try to do this problem just looking at these numbers, you'll probably get it wrong.
Yeah, and you'll start plugging in numbers where they don't even go, or you'll start creating ratios and different things that don't even make sense. So what we kind of learned in class over the past few weeks is things about ratios. So I'm going to kind of set up some ratios. I'm going to compare this side here, so how tall the girl is, to how tall this lamppost is. Okay, so we want
Well, you know, Ms. Bratcher, before you jump into that, can I answer your question?
Yes.
Are these even similar?
That's a really good point. So the first thing we need to look at is these 2 triangles. So we have one triangle here, this triangle right here, and the girl is standing perpendicular, so it's at a 90-degree angle.
Is that a safe thing to assume in future problems too?
Yes. That as long as the person or object is standing there at the ground, then it is a 90-degree angle since they are perpendicular.
Right on.
So this is the lamppost, and this is at 90 degrees. And if you see in our diagram, this angle right here, they share this angle. So these are also congruent. So just here alone, I can stop saying that this is congruent by angle, angle. So both of the triangles are similar, so we can proceed in creating or finding what x is, how tall the lamppost is. Okay, so now I'm going to create these ratios here between the smaller triangle and the larger triangle. So we have the side of the small and the side of the large triangle. And I'm going to set that equal to these sides. So this is going to be the bottom of the small over the bottom of the large triangle. Okay? So as I do this, the side of the small triangle is 160, and the side of the long triangle is x. And we saw many people today in class take, for this, 90 for the small, or the bottom of the small triangle, and many people put 360 right here. But this is incorrect because we're wanting the full bottom triangle. So it's all of that.
Yeah, so like on these two triangles on the right, the green ones, if you were to relabel them, the bottom would be 360. The bottom would be what, 450?
Yes, so it'd be the 90 plus the 360.
All right. So the idea of finding them similar in terms of triangles first kind of emphasizes the fact that we're looking at whole pieces here. So it kind of makes sense when you see like that SS, SL, the LB, and the SB. So you're talking about like, okay, small triangle left, big triangle right, small over large, small over large.
Yes.
Okay.
And then from here we're going to go ahead and cross multiply.
Oh, that algebra.
Yeah. 160 times 450. And then 90 times x.
Oh. Calculator assist, hold on. I got you.
Okay.
Maybe. Oh no, not Wikipedia. There it is. All right, so 450 times 160 times 160 is 72,000.
Okay, and then now we're going to solve for x, so divide both sides by 90, and x equals
800.
800, yeah.
Which is a pretty reasonable answer. I mean, if you think about the lamppost compared to human being, you're talking being like 4 times larger, 4 times taller. I think that's totally reasonable. All right. So it seems to me like these problems aren't so bad if you would take some time to prove some similarity and then kind of think about where the pieces actually lie, breaking up your triangle, so to speak.
Correct.
All right.
Make sure you guys draw pictures if you are given a task like this.
Pictures. Love it. All right. So we were dealing with area. We were kind of tongue-in-cheek during your little relay race about what's going on, but most of you guys figured out really what's happening. And that's if we're talking about area, it's no longer a K factor, but it's a K factor squared. So if I have some object with some area, if I multiply it by a squared K factor, I'm going to get my new area. Let's call it A prime. So if I have this rectangle with lengths 2 and 4, call it 2, 4, and then of course 2, 4. The area of this, of course, will be 8. This rectangle, whoa, hello, will be 8. K factor is 3. That's an important thing to know because that's going to define the size of my larger triangle, which I shall make in blue. That'll be what, 6, 12, 6, 12. So the area in this particular case would be 6 times 12 is what, 72? Right. So of course 8 times 3 isn't 72, but if you consider that this is the rule you guys extracted, and k squared becomes 9, you can definitely see that this 8 times k factor of 9 gives me the 72. And we'll take an opportunity later on to apply it, but that's definitely a rule that you're going to want to know. So k factor affects side length, so it's like the squared k factor affects the area. Man, that's some valuable information for a test, don't you think?
I agree.
So we can extend it. So let's say we have this rectangular prism with side lengths 2, 4, and 5. So 2, 4, and a prism is 3-dimensional. Look at that. Look at that beautiful drawing. 2, 4, and 5. Now, we're obviously talking about the volume in this particular case. And if you didn't remember, it's just 2 times 4 times 5. Let's see, that'd be 10, so that'd be 40. Cubic, whatever. The k factor defined here is 2. So let's consider that. If k squared is the area, then k cubed is going to be the volume. Okay, so that's actually going to give us an 8. We can test that, of course. With a k factor of 2, the side lengths will be doubled, so it'll be over 8 and 10. And then if I consider the volume, 4 times 8 is 32 times 10 should be 320. Which again, if you just use your rule, 40 times 8 is 320. So we have this this idea that we have this volume and multiply by the cube K factor, I'll get my new volume. Okay? Now, if that blew your mind, and it shouldn't, it's actually a pretty easy way to show this as a case. Now, this isn't technically the proof, but it's enough to kind of make you understand what's going on. So let's consider, if we would, just a rectangle. And let's call the rectangle side x and y. Okay? So if I choose some K factor, let's just call it A, just to make it really easy. And I want to look at 3 different things, the perimeter, volume, and area. We can kind of see how the K factor is supposed to affect it. So if we think about the perimeter of this new shape, if the K factor is A, and the side length is x, this should be x times A. Likewise, this should be x times A, this should be y times A, and that should be y times A. So if I think about the perimeter of this object, of P prime, which is our new perimeter, right? We have x times A plus x times A plus x times A. Nope. So, sorry, x times A, y times A, this is a 4 side lengths, plus x times A plus y times A. So let's do a little fancy algebra here, shall we? Let's take out this common term of A. So P prime is equal to A times the quantity x plus y plus x plus y. Now x plus y plus x plus y is a perimeter over here. So by substitution, our new perimeter is going to be our old perimeter times just our K factor, which we chose to be A. Okay? So if we keep continuing that idea, and now we consider area, okay? Still with the K factor of A, still with the same rectangle, x times A, y times A. This new area is going to be A times x times y times A, just the 2 sides being multiplied. Again, a little fancy algebra. A prime will just be common factor of A, x times y, which if you consider your original rectangle, the area here is x times y. So that means our area by substitution is our K factor, oh, shoot, it should be squared, shouldn't it? Squared. Should be squared. A times A is A squared. Times x times y, which is our area.
It's A.
Oh, it's A. Yeah.
Yep.
I'm probably using too many A's there, and I'm sorry for that. Okay. So there is a way you can explain it, and that's by again looking at the fact that when you multiply for area, you multiply A twice, hence squaring, and of course it'll solve volume as well.
Mm-hmm.
All right. Last one. So here's a typical problem, setting up using proportions. And just like the last one, we probably have to establish similarity first.
Correct.
So what do you think of this, Bradshaw? Are these similar?
I don't know. They look similar, but I think we should clarify by maybe a shortcut.
Yeah, no, I like that. Let me ask you a question first. And this is a question I'm actually asking the kiddos here. How many triangles do you see? You know what most kids will say, right?
2.
2. They say 2. Of course, they'd be wrong.
Mm-hmm.
Because the real answer is 3.
Correct.
We got this little guy on the right, we got this medium guy on the left, and of course we have this big guy, and that's the entire triangle, MAT. So this is strange because we actually have 3 triangles we're comparing then, right?
Correct.
Now you were talking shortcuts. Like, talk to me about that. Like, what are you talking about shortcuts?
Well, just kind of see if we can maybe use angle, side, side. Trying to think of some other ones that we came up with.
Side.
Yep, side.
I don't see a way that side or side is going to work because we just don't have enough information. Like we have 8 and 10, which kind of covers tiny triangle, but not the other 2.
Yeah, so maybe we should look more at the angles, see if the angles are way to tell similarity.
I agree. Here's what I'm seeing, Ms. Bratcher. I see this 40-degree angle over at M. I'm seeing this right angle at H. That tells me that this guy's got to be 50 degrees.
Mm-hmm. And then we can see at angle A, that's 90 degrees. 90 minus 50 is 40.
Okay, whoa, wait a minute. That's a 40-degree angle, that's a 40-degree angle. I think we got similarity.
So then angle T has to be 50.
Wait a minute. So we got 3 triangles, but everything's using the same angle?
Yeah, that's strange.
So that's gotta be similar, right?
It has to be.
So if it's similar, and I think we have enough information here to prove it, I think all we have to do is just kind of to look at our picture and see if we can actually set up some nice ratios. I'm going to use your strategy, Mrs. Bratcher, because I liked it, where you took the triangles and you kind of redrew them, except I'm going to cheat since I planned ahead, and I'm not going to redraw these, but instead I'm going to do this. Whoa! Okay, so see that again? We'll see that. So that's a little triangle on the right. Bam! I'm just going to pull it off, so that's now the triangle separate. I'll do the same thing for Mr. Medium here. That comes off. Of course, we have that here as well. Now, these are not aligned correctly, it seems. It seems like we lost at least one measurement here somehow. Okay, but let's see. If I take this guy and I flip left, right, and then maybe I do a rotation. There we go. And then take this guy, do a little rotation. I think that's a little bit more obvious. I think now we definitely have 3 triangles, and then if we fill in some missing pieces, that's going to be 50.
Or 8.
And that one side link is 8. Ms. Bratcher, I think we're good to go. I think we can actually solve this. I just mean if we set up the right ratios, we can actually solve.
Yes.
Now, it seems to me like I actually want to start here, because I know the most about this triangle.
You know, 2 side lengths.
Okay, so definitely find the third Pythagorean theorem.
Yep.
Okay. Cheating, it's going to be 6. Okay? But check that using the Pythagorean theorem, you see we're right. This is great. We can set up some ratios here. So let's do this. I'm going to start just using variables. Let's go x, y, z, w.
Yep.
Okay? So I'm going to start with this. And so I know that 10, which is like the hypotenuse. Actually, let's go ahead and use that. So I know the hypotenuse of the smallest triangle to say like the bottom of the smallest triangle has to be the same as the ratios elsewhere.
So we can use, on the medium-sized triangle, MA as x for like the hypotenuse of the medium triangle.
Yes.
And then we have the bottom for the medium triangle.
Okay. And it seems to me as long as we're keeping those things aligned, we can write these ratios all day.
Yes.
Okay. So let's attack this. Like, which one do you think you want to solve? The big triangle or the medium one?
Let's go with the medium one.
Okay. So we know we got to compare it to the smallest triangle, right? And I'm looking at the medium triangle, and I see I already have this 8.
Yep.
So what do you think? Hypotenuse or the bottom?
Let's go with hypotenuse.
Okay, so I know the hypotenuse of the medium to say the side of the medium has to be in the same ratio as a similar cousin over the tiny triangle diameter here. The hypotenuse of the small to the side of the small.
Okay.
And it seems to me, so the left-hand side is a medium triangle, right-hand side is a small triangle, hypotenuse is on top, sides on the bottom. Look okay to you?
Looks good.
All right, so we'll start pulling numbers then. So hypotenuse medium is x, side is 8. Looking at our triangle over here, we have what, 10 and 6. So it's just a matter of solving this guy. Okay, so we can do some cross multiplication. 6x is equal to 80. So x is equal to, C goes in there once, twice. What do we got?
13 and a third.
13 and a third. So we'll go through repeating. We knocked out x, so let's knock out y.
Okay.
Okay, so let's do kind of the same thing. We got side of the medium over bottom of the medium. So that should be side small, bottom small. Okay, so medium on left, small on right, side over bottom, I think we're good. So what will that be? 8 over y is equal to side small 6
6 over 8.
is 8. All right. So again, let's do some cross multiplying. 6y is equal to 64. So y is equal to? Not a nice number.
10 and 2/3.
10 2/3. 10.6 repeating. All right. We're cooking right along. Let's solve this guy.
Okay.
So big triangle time. Again, we have the side here, so I'm going to go side of big over hypotenuse of big, compared to our small triangle, side of small, hypotenuse of small. Now, Mrs. Bratcher, does it really matter what ratio I write here? So like I chose to write like side of big to hypotenuse of big.
No, it doesn't matter what order you go in, as long as you're making sure that you're relating the same things across triangles.
So like big on left, small on right, side on top, hypotenuse on bottom. Awesome. So let's go with some numbers. So side of the big triangle is 10. Hypotenuse is z, which we're trying to find. What's that? 6 over 10. All right. So that'd be 6z is the same as 100, meaning z is
16 and 2/3.
16.6 repeating. Oh, we're cooking right along. We got one more, Mr. Bratcher. We're almost done. We need to solve for w, the bottom. So I'm going to go bottom of the big to bottom of the small, and that'll be side of the big, side of the small. Okay? So I'm taking your advice. I'm changing up a little bit. So we went big triangle on top, little triangle on bottom. So bottom big is W, bottom of the small is 8, side of the big is 10, side of the small is 6. So 6W is equal to 80. So I bet X is 13.3.
Yep.
Which we found in the first one. Which we should expect some overlapping because these triangles overlap, right? All right. Wow. So much we covered.
Yes.
So it seems to me the moral of the story, although there's a lot going on here, is really if you separate your triangles and keep your ratios straight, you can find the values not so hard. So it seems over here there is a reason why you multiply the k factor squared for the area and the k factor cubed for the volume. And oops. Uh-oh. It's gone. Gone! Oh, I found it. And it seems to me the moral of your story was draw your pictures, separate your information, keep your ratios straight.
Correct.
All right. So guys, hope that helped. Hopefully gave you some hints of some stuff that you really need to practice. Mrs. Brash, do you have anything else?
Make sure you guys are working hard, and you should receive a good grade.
Yeah, now get out of here. Bam!